And Zach, take it away.
So this is our senior design presentation. We're team 23. We're building a 3D cementitious material printer. This is our team, Arturo, son, I'm Zach, Siggy, and Jason. So I'll be doing the background and objectives. Art will be doing the mechanical components, overview, and testing. Sun will be doing the mechanical current and future progress. Siggy will be doing the electrical components and overview. Jason will be doing the electrical operation and testing, and I'll be doing the conclusion. So the background for 3D printing of cementitious materials. 3D printing has been used to build structures which are more affordable than building with regular materials. The structures can be highly customized. 3D printers are also being used in space and are planned to be used on future missions. Okay, our objective was to build a 3D printer with a 10 by 10 by 10 foot print area. The printer is to be of a modular design, which is easy to assemble and disassemble. And the printer will have the ability to print various cementitious materials.
Okay, and I'll be going over the large gantry equipment and the overview of all the components that we utilize for this project. As you can see in the upper right-hand corner, this was our initial design that we worked on last semester and what we were planning to build this semester. Just below that is the actual SolidWorks concept design that we built. And as you can see, it's made up of 7 12-inch wide, 10-foot long trusses, each one capable of supporting about 1,540 pounds. Just to the right of that is the timing belt that we were going to utilize to move our gantry system in the X and Y direction, followed by the linear rails and the bearings that we were using to be able to make everything move properly, both X, Y, and the Z direction as well. Next to that is the tooth idler pulleys and the tensioners that we were utilizing, followed by the NEMA 34 high torque motors. We have a total of 3 for this design. One is for the X axis, one for the Y axis, and one for the Z. And follow that is the actual trusses, some pictures of the trusses that we were utilizing. Here's some more of the components for the actual design. So to the left, we have the actual rack and pinion gearing system that we were utilizing, 6.35 teeth per inch with a 20-degree pressure angle. Just to the right of that is the extruder with the NEMA 17 motor that we were utilizing, and this was going to be what was extruding the product or the cementitious product for our design, similar to the picture that Zach showed earlier, where you can see the actual concrete extruding out and actually printing. To the right of that is the 3x4 by 120-inch aluminum Z-axis tubing. And like Zach mentioned, our design is to build a gantry that is 10 feet by 10 feet by 10 feet tall. So we need a pretty tall piece of aluminum to be able to help us guide the extruder up and down in the Z-axis. And then finally is our pump. So this is something that we were going to purchase. I believe the university was going to purchase this in cooperation with the help of the materials science department, or the materials engineering department, sorry. And this is what we were going to be using to pump the material through our extruder. It's a 1 horsepower motor pump. It operates off of 110 volts. And again, this pump is designed for cementitious products. And again, this is what we were going to utilize to be able to pump the product to our extruder to be able to utilize our gantry. So here's a small video of our actual extruder, or sorry, our gantry design. So as you can see, it's moving in the X direction right now. You'll see the 2 motors that are on opposite ends. This is the Y direction movement. And then this is the Z axis movement. So again, that's that 3rd motor in our design. So the whole goal is to be able to allow this gantry system, similar to any 3D printer, to move in the X, Y, and Z directions to be able to print the concrete, and ultimately help us print some structures. Now, during this semester, we were working on some prototypes as we were not able to go on site to the university to actually build our gantry. We started off with a small gantry prototype, and we used these to be able to test the electrical code. So the ME students designed a Z-axis and an extruder system for the small little prototype that you can see on the upper right-hand corner. And later on in the presentation, you'll see a video of this actual small prototype in operation. On the bottom side there, you see the Z-axis motor mount that was designed in SolidWorks, followed by the actual assembly of it, which one of the students 3D printed, followed again by the extruder model that, again, was 3D printed, and it has a small NEMA 17 motor attached to it. And then finally, to the lower right-hand side is the final model of the small prototype that we built. And again, this was utilized by the EE team members to be able to test the code in a small concept at their house. This was a large gantry prototype, and I helped build this one. This is mimicking the actual Z-axis movement and the extruding system. On the upper right-hand corner is what we did. What we came up with to be able to use an extruder to actually print out the cementitious material. So you see some pictures of the initial concept, followed by the SolidWorks model that we built. And later on, you'll actually see the final product. On the lower hand portion of the slide here, you'll see the actual Z-axis and the extruder model initial design that we came up with, followed by the SolidWorks model, and ultimately the final build product that we were actually able to build utilizing the actual NEMA 34 motor and the rack and pinion system, along with the actual extruding system that we'll be using in our large gantry. So here are a few videos of the actual units in operation for this large gantry system. So on the upper left-hand corner is the final build product. And it kind of goes over the operation using the large NEMA 34 motor with the rack and pinion system. And it's moving up and down. Pretty self-explanatory. And that is our extruding system that you saw on the previous slide. Just to the right of that is an actual testing that was done late in the semester of this actual large prototype, lifting 100 pounds. And later on in the presentation, one of the EE team members is going to explain what they did to be able to get this to function. And then finally at the bottom is a small little extruder system in operation that we're using to actually extrude the concrete out. And for the final gantry model, it won't be moving that quick, but that's just for, again, testing purposes. And with that, I'll pass it on to San, who's going to go over our progress for this semester.
All right. I'll be going through the current and future progress. We were fortunately enough to be able to go back on campus and assemble a gantry in the makerspace. The first thing we did was to go, we get there is to go through our inventory, make a list of what we currently have, and write down what else is needed to be fabricated. We also went through the makerspace stockroom and see what scrap material we could use instead of buying brand new materials. Next slide, please. For the setup of the gantry, we used a step-by-step instruction that we have previously put together in the case that we weren't able to go back on campus. A graduate student or someone else who is allowed to go on campus could help us assemble the gantry. In this case, we were able to go back ourselves. This instruction came in handy, and we were able to quickly to start assemble our gantry. As you can see in figure 1 and 2, the first thing we did is to create a 2 carriage plate for the top truss using an aluminum plate, mounted to 4 linear bearings. The next part of this assembly is to design and mount that connects the linear rails to the truss, as you can see in figure 3. Next slide, please. We have designed 3 options on how to mount the linear rails to the truss. On figure 2, the red arrow shows the location of the mount needed throughout the whole gantry. For option 1, the pros is that it will preserve the truss by using the U-bolts. However, the cons is that it costs a lot more because we will need 9 aluminum plates and 36 U-bolts to mount at all 9 locations of the gantry. For option 2, the pros is that it will cost less because we will only need 9 aluminum plates with screws and bolts. But the cons is that it will need to be, the truss needs to be drilled through. Lastly, for the option 3, we could use the C channel and U-bolts. The pros is that we could preserve the truss, but the cons is that it will cost a lot more as require 36 U-bolts and at least 9-foot long C channel to mount at all 9 locations of the gantry. For this reason, for the reason of cost and time, or to obtain the material, we decide to go with option 3. Next slide, please. We were able to find the material needed to fabricate the Z-axis carriage plates, as you can see in figure 3. The carriage plate is made of aluminum and will be held together by welding the 90-degree aluminum angle to the 2 plates. The next steps to this is to mount the linear bearing onto the carriage plates like that in figure 2. Next slide, please. We have gathered some material needed to finalize the Z-axis. The plan is to mount the rack and the linear rails onto the 4-foot aluminum tube and use this for testing purpose before we actually raise the whole gantry to 10 foot high. Next slide, please. And then this table is a list of material that we will needed to finalize the gantry. We list out all the costs for each item and provide a website on where to purchase this item. The website is just not shown here, but we do have it. Some of the items are included are the linear rails, linear bearings, tensioners, pulley, pinion gear rack, and motor racks. Motor brackets, sorry. And I'll pass it on to Siggy for the electrical parts.
All right, then. Continuing on to the electrical part of the project, we're first going to talk about Marlin Firmware. Marlin Firmware is an open source code which is utilized by numerous 3D printers as well as CNC machines and laser cutter applications. As you can see on figure 1, Marlin Firmware operates based off an Arduino Mega, which is the blue board, and then a RAMS 1.4 board. These boards are stacked one on top of one another, which will create an ideal board we need to use to operate our motors. Marlin Firmware also has integrated Gcode commands, and these commands are utilized to either disable certain functions of the code or redefine other functions such as stepping size from millimeters to inches, or maybe disable certain functions. Marlin Firmware is also utilized to define the printer parameters such as the bed size, the amount of steps, the type of drivers we're utilizing, and other commands as well. If you could move on to the next slide. Going back to Gcode commands, as we could see here on figure 1 and 2, figure 1 is talking about Marlin temperature coding, and this code was actually utilized for FDM printers, which talk about cold extrusion. So let's say for some reason you're trying to print, but it hasn't warmed up to a certain temperature, then it won't allow you to print. This actually gets in the way of our printer, because since we're not really utilizing temperature, since we're going based off cement, this setting could actually not allow our extruder to print at all. So in figure 2, as you could see, this M302S0 command is actually utilized to prevent this cold extrusion. It's actually a Gcode command which will disable cold extrusion. Going on the figures, as we could see in figure 3, these are actually the axis steps per unit, and these are utilized to define the amount of steps that the motors will take. And based off that one, there's also another Gcode command which is utilized, which is the inch mode support. This support feature will defined from millimeters to inches. Okay. As you could see here on the image to the right, this is actually the wiring schematic that we used for our printer. It's based off an Arduino Mega, as I said earlier, the RAM's 1.4. The big motors which we're utilizing are NEMA 34s, but these actually require a driver, which is the DQ860MA. For this printer, we need three NEMA 34 motors. We also need a 60-volt power supply. And depending on, let's say, since we're going to get into a prototype model we built and the large scale, depending on which one we're talking about, we actually need different drivers and motors from one another. Okay, next slide. Okay, so now let's first start off with the X, Y, Z axis and the large scale motors. The large scale printer is actually dependent on three NEMA 34 motors. As I said earlier, the NEMA 34 motors operates based off the DQ860MA driver, which is seen in figure 2. This driver is rated from 24 volts to 80 volts. And as you could see here on the figure 1, there's the NEMA 34. It's based off a 6.8 amp amperature. And as you could see here on figure number 2, we actually need to flip certain amount of switches. So then that way we could get the current we need for the motor. As I put a red arrow, which is the 6.4 amp to 6.4 amps. And then from there, you have to switch the switches. That way you get the required current. For the large motors, we also require a 60-volt power supply. And as I said before, this is operated based off the Arduino and RAM's configuration. And to power this Arduino and RAM's board, you actually require a 12-volt power supply. Okay, next slide. Now for the large scale, we actually require a different amount of motor and driver to drive the motor. This is based off a NEMA 23 stepper motor. The NEMA 23 stepper motor actually requires a similar driver such as the DQ860, but it's actually rated at much lower DC voltage. For this driver, we actually, since it's rated from 9 to 42 volts, we could actually utilize the 12-volt power supply that we were using for the RAM's 1.4 configuration. And as the previous slide, this motor is rated at 2.8 amps, and I put a little arrow to show which switches had to be toggled to get that current. Okay. Now I'm going to talk about a prototype model that we use. This prototype model actually runs off of 4 NEMA 17 motors, which actually operate the whole printer. For this NEMA 17, we actually only require one power supply, which is the 12-volt power supply powering the RAM's 1.4 board. These motors utilize a A9888 stepper motor driver, and these drivers actually go on the RAM's 1.4 board, as could see in figure 3. These boards have a certain selected sides where they're going to connect, and then from there we have to pin it depending on the motor requirements. Okay, next slide. And now I'll pass it on to Jason for testing and electrical operation.
So following from what Siggy was mentioning and the group, we are going to be covering the electrical operation and testing. Next slide. So over here is a very simple basic schematics of how the prototype on the left differs from the full-scale model on the right. You can see that both models are very similar in regards to the only thing that differentiates the two boards from one another is that the full scale requires power supplies before the motors. And they also do include drivers that need to be attached alongside the motors and the drivers. Control boards are all maintained. Next slide. So the video on the left is one of our first trial runs. It basically simulates the prototype printer printing a square using a Sharpie marker. Once we have determined that the code and the hardware has been optimized fully. By this we mean like it doesn't shake too much or it doesn't throw too many artifacts. We move on to a sand-based print mixture. In this case, it's just sand passing through a tube. And from this test, we're able to conclude, you know, if the prototype is set, it's ready, we can move on and work with our full scale. So here are the videos again, showing the two tests. The sand mixture on the right, it's just basic play sand, but it's printing at a thickness of roughly around 2 to 3 millimeters. As you can see, the lines come out straight, clean, and there's no jagged movements. Over here, since we do not have a fully operational gantry or printer machine yet, fully configured, the closest simulation we could run is to run independent motor tests using the X and Y motors independently. These are just basic runs using Pronterface, or the user interface that allows us humans to interact with the printer itself. This test right here is shown to, we're basically giving direction to the printer, and it's essentially telling the motors to move a certain distance. Over here on the left side, the extruder and Z-axis mechanism is installed on our miniature prototype. You can see that on the laptop, we are using our Pronterface program, and we are sending commands to our miniature printer. You can see that at the beginning, the Z-axis moves up ever so slightly, and over here the extruder screws when it's toggled. On the right side, this is our full-scale extruder test. You might have seen this one in our earlier slide. And basically, we were running trial runs on varying extrusion speed. This one happened to be one of the best results, having it run at really fast speed, but it will run quite well at slow and medium speeds. So over here, the video will load. This is the full-scale Z-motion testing. Prior to this semester starting, in the fall semester, we gathered information from the data sheets, and we concluded that the NEMA 34 motors that we are using should be able to handle a should be able to lift a weight of about 200 pounds. Overall, our gantry and Z-axis mechanism shouldn't weigh more than 100 pounds. So as a simulation, we were able to attach varying weights up to 100 pounds and run a few tests. So you can see in this video all the weights attached, and actually it runs pretty flawlessly. The motor showed no signs of struggling, and honestly, it could go for more weight if we needed to add more weight to the printer later on. And finally, I will pass it back to Zach, and he will end with a conclusion.
So the team has designed a full-scale printer as well as a small prototype, which was used for the testing. We came up with 3 options, and we proposed them to mount the gantry together with the linear rails. The team has put together a final list of parts we need, as well as a guide to assemble the printer. And thank you for watching our presentation.